And I found that Pythagoras philosophized that the universe was made of vibrations, and he did this just from observing that, like, simply when you pluck a string, the longer the string is, the lower the note is. He realized that every single physical material thing around us makes some type of sound and has a correlating sound that is matching with it. Around that same time, it was like between 470 and 590 BC, Democritus and Leucippus were theorizing that the universe is made up of particles, and they were trying to discover a fundamental particle of reality. And that was where, around that time, is where the term atom came from, atomos, because the word in Greek, the word atomos means uncuttable. And we're going to see how philosophies manifest themselves through scientific research over time. When you hear like the standard model of particle physics, even in my mind, something like that, I imagine they're approaching it from a strictly material perspective, but that's not the case. The more you learn about particle physics, the more you'll realize that waves and frequencies and hidden dimensions and fields, quantum fields, are inseparable from particle theory. They go hand in hand. Even a lot of particle physicists, from their perspective, they still describe the universe as fundamentally being vibrations. And that's what, honestly, that's what all of this is about. That's what the sacred geometry video is about. And a lot of you who know me know that that's what I refer back to a lot, is the fundamental nature of things. I feel like that those are the biggest questions for humanity to ask. Trying to understand reality at its most fundamental form. And then if you think about the potential of us living in like a fractal universe or a fractal holographic type of universe, then in that sense, that's why we feel like there is no beginning and no end. And we're just constantly going on this loop, but we're rising, just like the golden spiral. Definitely evidence of ancient African tribes studying cymatic formations by putting grains or sand or different types of seeds on top of drums and then beating those drums in certain ways, and then they would read prophecies of the future from the shapes on those drums. Physics is almost like the harmonies, chemistry is like the melodies, and the entire universe is like a symphony of vibrations. That's a great analogy for me. It's like an infinite cosmic field of dancing vibrations, a looping symphony. And within that is separate vibrations that have distinguishable traits. But together it is just a field of vibrations. Every photon creates an electromagnetic field, and these waves oscillate together at the speed of light. We don't see the entire electromagnetic spectrum. We all know that. We can only perceive only about 430 hertz to 770 terahertz. And with other instruments, we can detect a broader spectrum. But literally, there is no reason to believe that spectrum doesn't continue in both directions. We can only detect the electromagnetic spectrum as far as our tools will let us measure it, whether those tools are our eyes or other instruments. Our understanding of the electromagnetic spectrum is completely limited by our biology and our technology. Is there a mass collective conscious increase going on, and is there some formal resistance to it? Very, very likely. But water will find its way back to its source, one way or another. As much resistance as we feel, that's what we're here for. And some of the resistance is necessary. Trees got to grow through the dirt in order to get strong enough, and they got to fight against the wind to get strong enough to grow big and fruitful. And I'm not saying that I'm some strong tree or anything. I'm just saying these concepts in general. A lot of people think that the scientists are trying to take the magic out of reality, but obviously I think that through understanding that science, you uncover the true magic and the true mystery. And the more we learn, I think the more that is evident. I heard that actually recently, that CERN is why we have the internet, because people wonder why we spent like $9 billion on something that doesn't have a direct benefit to humanity. But as we know, through scientific innovation, there's multiple indirect benefits that we get from it. The rigorous approach that the scientific community has to some of these ideas, a lot of people don't like it, but I think it's necessary, and that's actually caused people to dig farther and confirm even more amazing things. I want to talk about just the basics of the standard model of particle physics. Scientists say it is the most successful model in physics. There's going to be a lot of unknowns still. It doesn't mean that there's nothing left to learn about it. Most of this reality is not material. So the standard model of particle physics is extremely successful and extremely useful. It's a very useful tool in trying to understand reality in general, but it's not the end-all be-all theory here, and we'll see why. Because I don't like the name, the standard model of particle physics, but the first notion in particle physics is wave-particle duality, as we talked about before, that every particle has a corresponding wave to go along with it, and these waves ripple out like waves on a pond. So an electron creates an electron wave in that field. All particles are one of two things. They're either fermions or they're bosons. The fermions are the actual physical particles in their predicted state. That is the fermions. So when we talk about those are the protons, the electrons, the neutrons. The bosons are the energy or the force particles. So in particle physics, they give every single force, every measurable force, its own particle. They believe that these bosons are their own particles that generate the force that acts between the fermions, which are the solid particles. The main difference between fermions and bosons is that they have a reversed spin. So what makes the difference between a force particle and the actual physical matter particle is the direction of its spin. There's 4 fundamental forces in the universe: electromagnetism, gravity, strong nuclear force, and weak nuclear force. Electromagnetism, as we understand, that's electrons giving rise to electric fields. Gravity is the weakest force in particle physics. A lot of us think of gravity as being able to control these giant bodies in space, but on a quantum level, gravity actually has almost no measurable force, and then you have the strong nuclear force. And this is what binds the quarks together within an atom. You have electromagnetism, gravity, strong nuclear force, and then you have the weak nuclear force. It's so weak it's tough to measure, but they know that it's responsible for radioactive decay, and it allows quarks to switch identity. So it allows neutrons to switch into protons and things like this. Gravity is the weakest force in particle physics, which is interesting because a lot of us think of gravity as being able to control these giant bodies in space, but on a quantum level, gravity actually has almost no measurable force at this level. That's one of the things that we're still trying to bridge in particle physics, is the connection between gravity on a massive scale and how it can be reduced or quantized on a small scale. So that's another one of the unknowns still, but gravity is still, it's just very weak, but on the quantum scale it is still a measurable force. So, and we'll talk about that later, I'm going to bring that back. They're trying to either gravitize quantum mechanics or they're trying to quantize gravity to bridge the two. The standard model of particle physics still doesn't do that. There may be a force-carrying particle for gravity. Physicists are working on linking a particle to gravity. There's a theoretical particle that would be like the force carrier. Gravity creates a bend in space-time. Scientists aren't happy with that explanation, although Einstein's general theory of relativity has been proven by watching light bend around other bodies in space. We know that the theory of relativity is true and that these massive objects do create curvature in space-time, and that's what creates gravity. that doesn't account for the actual force, what actually causes them to be sucked into that. What is that force carrying particle? Because from the perspective of particle physics, they believe that every force has a corresponding particle. They theorize, and this is speculation here, but it is ongoing research in this field, that there is a graviton is the name for the force carrying particle for gravity. But I'm going to get into the difference between dark matter, antimatter, and dark energy, because there is fundamental differences. These terms get used interchangeably, and a lot of times it's wrong. Dark matter would be the particles, the corresponding particles that don't interact with electromagnetism. Dark energy is literally the force. It makes up at least 60% of the energy in our universe. We know it's there. It doesn't interact with electromagnetism. It's really tough to measure it. It has almost no mass. We can see the effects of it, but we can't directly observe it. Antimatter is something entirely different. Every particle of matter can have a directly corresponding particle that is the equivalent in mass, but the opposite electrical charge. As soon as it interacts with its corresponding particle, it is annihilated. And physicists say this is when they're both converted into pure energy. This is what binds the quarks together within an atom. The strong nuclear force. Now the carrier particle for this force, they're called gluons. Almost like glue, because they literally hold these quarks together within these particles. So again, these are not matter particles. These are particles of force. The fermions, or the matter particles, would be the quarks in this case, and the force-carrying particles are the gluons in the strong nuclear force. They create what's known as a gluon field. And every single particle creates a corresponding field in this fabric of space-time, pictured as a circle, and they start reaching out with these little flux tubes with these lines that come off of them. And these lines will continue until they find another gluon to stick to, another corresponding particle with a gluon to stick to. A lot of that just mimics the sacred geometry that we talked about. A great idea in particle physics is supersymmetry. That's just the idea that every particle has a partner particle with an opposite spin. When the scientists insert supersymmetry into the standard model of particle physics, it solves a lot of the mysteries, one of them being like the difference in mass between the Higgs boson and other bosons is astronomically huge. So they're trying to figure out how can the Higgs boson have so much more mass than every other boson. They're missing something there. Supersymmetry would explain this perfectly, and it makes the equations work out. It would also explain the dark matter. Now, when they insert supersymmetry into the standard model, they believe that all of these weak interacting particles would likely have their own bosons that would exist, but we just can't directly observe them yet. I want to talk about guts and toes, and that would be grand unified theories and theories of everything. This is where we start getting more into the speculative field and the more muddy waters. I do think it's interesting that a lot of the former ideas were once those speculative ideas that a lot of people didn't want to accept, and over time they end up being well established and proven. Standard model of particle physics hasn't been directly connected to Einstein's general relativity. We know the general theory of relativity is successful. We know the standard model of particle physics is successful. How do you bridge the gap between the two? String theory says that space-time is smooth until acted upon, and it says everything that we know of as reality is just these tiny vibrating strings. String theory inserts extra dimensions into the standard model of particle physics, and that makes it cohesive with Einstein's general relativity. Through observing just what happens to light in a black hole, they realize that these things break down infinitely, and really the best equations show a singularity, an infinite loop of dimensions. Since then, they've expanded on that to what's known as superstring theory, and then on top of that, they expanded that even more to the membrane theory, or the M theory. What if it's infinite? You know, that's unsettling to a lot of scientists. They want a measurable beginning and end. Depending on how far you want to take it, they have the same basic underlying principle. Loop quantum gravity is the geometry of space-time and particles. Is that the fabric of space-time is granular, not smooth, and that it's made up of tiny loops that are woven together in a network. This also bridges the gap between particle physics and general relativity. It does solve that problem, and it doesn't have to include extra dimensions. So it doesn't, to them, that solves that problem of just inserting these implied extra dimensions. And it also doesn't need new elementary particles to explain, but when they try to make it compatible with general relativity on other scales in between the quantum and the cosmic, it doesn't add up. So it's still loop quantum gravity. It's not widely accepted. String theory is more widely accepted, but a lot of theoretical physicists are trying to bridge the two theories into one. Neutrinos are another particle that we know of for sure that exists. And these neutrinos don't interact with electromagnetism. There's almost no interaction with electromagnetism, so it's tough to detect them. There's different ways that they've measured them, but they know that neutrinos exist, and they know that they're zooming through the universe at all times. I don't remember the exact number, but it was something like 90 million of them pass through you every second. Okay, so apparently it's actually more like 200 trillion zoom through our bodies every second. What information is contained in them? We still don't really know. They're actually called ghost particles because they're so elusive. If 95% of our universe is comprised of the combination of dark matter and dark energy, that is undetectable directly. We can only detect it from the effect that it has on the known forces and the known particles. So where do dreams exist? Do they exist in the dark matter? If every piece of dark matter has its own symmetrical particle and they have their own bosons, that is an entire reality. So far we only perceive reality through our senses. We can only detect the electromagnetic spectrum as far as our tools will let us measure it, whether those tools are our eyes or other instruments. Our understanding of the electromagnetic spectrum is completely limited by our biology and our technology. What exists outside of our detection, and how do we tune into that? People are like, dreams aren't real. Where do dreams exist? Some people think they only exist inside of our mind. Well, and how could this information be out there, be actually in an actual location without us realizing it? Where is this information that we're tapping into? Even if you want to talk about like communicating telepathically with people, or where do these ghosts exist and where are they talking to us from, and how could they possibly be out there? If we don't see them, we would feel them in some way. Well, we have massive, incredible amounts of information flying around us at all times through Wi-Fi, through satellites. And we know that, the things that we see on the internet, they're wireless. This information exists in between our devices, but it's undetectable, but it's out there. Think about all of the information that's traveling around wirelessly. This video is actually in the atmosphere, between all of our devices and the satellites around this world. This video that we're watching right now, my audio and all of the information contained in it is not just here in the cell phone. It's being transmitted. It exists right around us, right through us. You just have to have the right tool to view that, to pull that into your perception. Schrödinger equations in quantum mechanics describes waves as a probabilistic outcome. Every particle exists as a quantum wave function. Every particle has its field, and that field creates a probability of outcomes of where that particle can be measured. There's different established theories. The most widely accepted is the Copenhagen Interpretation, which is probably what most people have heard about. And that suggests that wave functions collapse when the measurement is made on them. They don't actually snap into reality until you measure them. The Schrödinger equations are used actually in the Copenhagen interpretation to describe the probability of where that particle is going to be when you measure it. It describes the wave function and how it will evolve probabilistically. Then there's also, it's not as widely accepted as the Copenhagen interpretation, but I also thought it was interesting was the pilot wave theory, or Bohmian mechanics, and that was proposed by David Bohm. That interpretation introduces a pilot wave, saying that these particles seem to exist in a superposition because they're clouded by this wave and the particles are carried by the wave. Copenhagen basically says that these particles don't exist in this dimension or this reality as either one until they're measured. The pilot wave theory just says that it's kind of blurry because of the wave, basically. The function of the wave is what influences the location of that particle. The many worlds interpretation. Every theory up to this point basically says that every particle has its field, and that field creates a probability of outcomes of where that particle can be measured. There's different theories on how we can reduce the location of that particle, which would be literally like what would snap our reality into existence, what would reduce the quantum wave function. Some things say it's not reduced until we measure it. Some things say that it's reduced over time based on the environment. Many worlds interpretation says that the wave function doesn't collapse. These particles don't snap into a single location. Many worlds says that when you observe it, all the other possible locations of that particle split into their own separate universes, and what we observe is just the particle in this version of this universe. There's multiple branches every time you try to measure a particle. Where do dreams exist? They exist somewhere besides in our head. Now that world is not big enough. Where does our imagination exist? Where is the collective consciousness? Where are these Akashic records? They're not directly within us and they're not directly without us. Dark energy makes up at least 60% of the energy in our universe. We know it's there. It doesn't interact with electromagnetism. We know it exists. We can see the effects of it, but we can't directly observe it. Antimatter is something entirely different. Every particle of matter can have a directly corresponding particle that is the equivalent in mass but the opposite electrical charge. We can only perceive 430 hertz to 770 terahertz, and with other instruments we can detect a broader spectrum. Where is this information that we're tapping into? And if you made it this far, I do appreciate it. You can search d.k space dream space keeper on just about any platform and find me for more information about things like this.